Hello and welcome to another video discussing physics and the mathematics thereof. So today we're going to be deriving the momentum operator. Now the prerequisites for this video is that you've done at least a little bit of quantum mechanics, that you've been introduced to some of the ideas. Some important ones: you should recognize this notation as the expectation value for the position, and this is the equation to solve for it. You should also be able to recognize this equation over here. This is just Schrodinger's equation for one dimension. And I'm going to be doing everything in one dimension just to keep it straightforward. And if you don't recognize these two equations, you at least need to have some faith in me that they are correct, and we can go on and do some cool things from there. But hopefully you have done some quantum mechanics before and you've seen these two equations. Now, to get the momentum operator, I'm going to start by finding the speed. In quantum mechanics, it's a little bit facetious to say speed. What we can talk about is the time derivative of the expectation value of the position. When someone is talking about speed, this is more likely what they're talking about, because if a particle doesn't have a well-defined position, how can they have a well-defined speed or trajectory? It doesn't even really make sense to say. But you can talk about how the expectation value of the position, or the average position, changes with time, which is what they're going to do. Now, if we're taking the time derivative of this, when we bring derivatives inside of an integral, they become partial derivatives. Alright, so continuing on, we can split this up. What does that really mean? Well, actually I'm going to do two things at once. First off, this is a partial derivative with respect to time, so the position has nothing to do with that. We can just pull that out of the integral, as well as I'm going to split this up. So that is going to give us the integral. All of these integrals are going to be over all of space, so I'm just going to drop the limits of integration and we'll bring them back when necessary, but it's from negative infinity to positive infinity. So we're going to have position, partial derivative with respect to time of, well, what does this mean? It means the conjugate of the wave function times the wave function itself. Alright, so we're going to use the product rule, and this is going to become the integral of position times the partial of the conjugate with respect to time times the original wave function plus the conjugated wave function times the time partial of the original wave function, dx. Now, the first time that I saw this is where I would have gotten stuck. We're not given any information about the wave function. As far as I knew at this point in studying quantum mechanics, you had to solve Schrodinger's equation to get the wave function, but we've been given no information about the potential, so how are we going to solve this? Well, we do use Schrodinger's equation, but another way to think about it is that Schrodinger's equation tells us how the wave function evolves with time. So I'm just going to divide both sides by I h bar, and we're going to get the partial with respect to time of psi, our wave function, and we can plug that into here. And we can conjugate it and plug that into there. So when you divide by I, that's the same as multiplying by negative I, so we can put that I up here and cancel out that negative sign. One of the h bars goes away, and we have 2m. And we have the second partial with respect to space of the wave function minus I over h bar times the potential energy times psi. So now we can just conjugate this entire equation. Okay, so we can plug that into our equation. It's going to get rather large, but we'll have some faith and it will simplify down quite nicely. Okay, so all I've done is plug in the time derivatives, the partial time derivative of the wave function conjugated and the wave function as prescribed by Schrodinger's equation. Now the first thing that's nice is these terms cancel out, which is great because we haven't been told anything about the potential. So now that it's gone from our equation, that's a good indicator that this will be quite general of a result. The first thing to do here, that is straightforward, is we can pull out these constants. Awesome. But solving this integral is not so straightforward. This is another place that I got stuck the first time that I ever saw this. You have to use a bit of a couple of tricks, and then even before we're done, we're going to use a couple more tricks. So what we're going to do next is we're going to use integration by parts on the integral as a whole. This is going to be our, if you're familiar with the u and v notation or whatever function names you might have used, I learned it as u and v. It's saying let u be x in this case. We remember integrating by parts, we get to integrate something and we get to differentiate something. We want to differentiate this x to make it go away, and we're going to integrate everything that's left over. How to integrate this is the tricky part. Oh, I dropped a minus sign. That will be very important in just a moment. So du is just dx. Awesome. So that went entirely as planned. Now dv, like I said, I learned with u and v. So dv, the thing we're going to integrate, is everything else. And it's how to integrate that that is the trick. Plus psi conjugated, the second partial with respect to space. Put brackets around that, and that has the dx. Now, in order to solve this, essentially what we're doing is integrating both sides of this. So what is this the derivative of? If I hadn't been shown this, it would have taken me a very long time to figure this out. What you end up thinking is there is a derivative, there's a second derivative on these two terms. Oh, sorry, that's supposed to be conjugated. There's a derivative on these two terms. There's not a derivative on here. What would happen if we, let's see if I can make a little aside for myself. If we took the partial with respect to space of these two, however, these are just going to be first derivatives. Everything else here will be the same. And hopefully we're going to get some cross terms that will cancel out, but it's one of those things you would never, well, I shouldn't say never, but it would take a very long time to come up with on your own. So it's good to see it done and keep it in your back pocket. So what's going to happen here? Well, first things first, we're going to get that second derivative we wanted. Awesome. Squared times psi. Then by the product rule, we're going to have minus the spatial partial of the conjugate times the spatial partial of the original wave function plus the spatial partial of the conjugate times the spatial partial. So that is looking good. These two terms are going to cancel out. Awesome. Plus, well, the thing that we wanted. Times the partial, the second partial with respect to space of the original wave function. And indeed, we find that the derivative of this guy right here gives us what's in here. So by the fundamental theorem of calculus, that is the answer to this. Remember, we're integrating here. So we find that v is simply what was in here, minus the partial with respect to space of the conjugate plus the conjugate times the partial with respect to space. So now that we've done that devious trick, we can plug that in here. You know what? I'm going to get a new sheet of paper because that will probably get a little messy. So let's see if we can leave that in view. So remember, this is our integral here. So we still have the constants out in the front. I h bar over 2m. And we used integration by parts. So we're going to have the boundary terms, which is x times minus the conjugate. Oh, sorry. This should be the original wave function in there. I just forgot to write that out. Coming back to the integral, it's going to be minus the partial with respect to space of the conjugate times the original wave function plus the conjugate times the partial with respect to space of the original wave function. Now that's the boundary term, so we're evaluating that. Remember, our limits of integration are over all of space, so negative infinity to positive infinity, minus the derivative of this is just dx, and the integral, as we found, was this nice term over here. So it's going to be minus the partial with respect to space of the conjugate times the original wave function plus the conjugate times the original wave function dx. Put some brackets around that if we want. Now, we have to use normalization to look at this boundary term. We know that all wave functions must be normalizable, which means that they must go to 0 at infinity. If the wave function exists everywhere and it doesn't go to 0 at infinity, it will be impossible to normalize it. Now, I'm going to do a bit of a hand-wavy argument, but if we think about how fast it goes to 0, it must go to 0 faster than a polynomial does. It's either going to be some sort of exponential or a linear combination of trigonometric functions, but for it to be normalizable, it's got to go to 0, and it's going to go to 0 faster than a polynomial, especially of degree 1. So when we take the limits, these are going to tend to 0 much faster than x is tending to infinity, and we can send this entire boundary term to 0. So clearing that up, we're going to have I h bar over 2m. I'm going to pull out this minus sign here, times the integral of minus the partial of the conjugate with respect to time times the original wave function plus the original wave function times the partial of psi with respect to space dx. I'm not going to put the brackets. Now we're almost done. As you can see, it's calmed down quite a bit. We really only have one more trick to do and we're done. It's using integration by parts to shift the derivative from this conjugate to the wave function. We'll be able to combine these, and similarly we'll throw away the boundary terms. So without going through all the details like I did last time, hopefully it's easier to see, we're just going to focus on this term. Remember that the sum of the integrals is the integral of the sums. So we can think of this as its own separate integral. If we let this be the thing we differentiate, this be the thing we integrate, it should be straightforward to see that the derivative shifts from the conjugate to the original wave function, and similarly to before, the boundary term goes away, the wave function and the conjugates go to 0, and the derivatives as well. So just going ahead, skipping a bunch of steps, remember, after you do integration by parts, you have to put a negative sign in front of your new integral, so that is going to cancel this negative sign. And, oops, sorry. So the derivative has now moved over to the other side. We have the partial, or not the other side, but the other term of, so we have the partial now of the wave function, and then added to the exact same thing. So that is really good news. Excuse the dog in the background. We can add these two terms, cancels out this 2, so think of that. And what we find is this, over m times the integral of the conjugate times the partial with respect to space. Now this is really interesting. A couple things we can do to clean it up. We could make this positive and move the I to the bottom. We can bring h bar over I inside here. What we have is the integral of the conjugate, and these are just constants, so we can bring them in. I'm actually going to leave the mass out in the front, and you'll see why in a second. H bar over I, and there's a derivative here. We can write that in these brackets, and we can think of that as an operator. This thing is operating on the wave function. We call this the expectation value of the speed. But really, that's just a definition we're making up. It's the time derivative of the expectation value of the position. How does the average position value change with time? Well, we found that that is 1 over m times the integral from negative infinity to infinity over all of space. And we have the conjugate of the wave function, h bar over I, partial with respect to space, and the wave function. And we can think of this as the speed operator. Now we can take this one step further by multiplying this whole thing by m. So that's going to cancel it out here, we're going to cancel it out here. And we can define that as the momentum operator. Well, this would be the expectation value of the momentum. So it's just, again, all of this multiplied by m. And so, sorry, the speed really should have, if you want the expectation value of the speed and you're thinking of the speed operator, the m really should be inside here. The m is part of the operator for the speed. Whereas for the momentum, this is what your operator is going to be, what I had before. I was skipping ahead of myself, sorry about that. So this is the expectation value of the momentum. In terms of what we were talking about before with the position, that would make this the momentum operator, and we give it a hat. A circumflex, not to be confused with a unit vector, but hopefully based on what you're doing, you can recognize the two of them. So we have found the momentum operator. We'll put a box around that because that's an important result. It took a couple of tricky applications of integration by parts, but in the end, we were able to work it out. But that's it. That is how you derive the momentum operator in quantum mechanics. I hope you found this useful, and I would really recommend that you start off with simply these two equations, just the Schrodinger equation and the definition of the expectation value for the position. Remember that you're taking the time derivative of it, and go forward and see if you can get yourself to the momentum operator. Thank you very much, and I'll catch you next time.